Hello everyone, welcome to the presentation of PSDoodle, Fast App Screen Search for Partial Screen Doodle. I am Shomik Mohia, PhD student at Computer Science and Engineering Department, University of Texas at Arlington. You are a software developer and try to find an Android app screen design with a menu icon at the top left. You use Google image search with this keyword and then you end up with a search result that few of them have a menu icon at the top left. For more complex query like a menu icon at the top left and image under it, the results become old. And you can see it is really hard to express this page structure or UI element positions. You can think of another approach like searching through Sketch. There is a state-of-the-art software that uses a pen and paper method where you draw with a pen on a paper, then take a snap and provide it to the software pipeline that uses a deep neural network and nearest neighbor to rank those search results. And as it uses Sketch, it's really easy to express those page structures. But problem with this software is it relies on a complete screen. And if you need to make any change, you have to do the whole screens again, then go through this pipeline. Thus, it becomes really slow and tedious and lose this interactiveness. Here comes PSDoodle, our approach, where it uses a interactive screen sketching approach, where you draw a one UI element like a menu icon at the top left, then within 2 seconds, it brings you app screens with menu at the correct position. Then you add an image there, then again it updates search results with menu and image at their corresponding position. So about background, we want to talk about Google Quick Draw and Doodle UINet. Google Quick Draw is a dataset of 50 million sketches representing 345 categories spanning from aircraft carrier to zigzag. It collected this drawing through a website where they told a user to draw one word prompt like draw a house, then user use their imagination. As user uses their imagination, it have a variety of drawing styles. These sketches are not raw pixels, but each drawings are represented through a straight line with their XY coordinates. The stroke is constitutes of sequence of lines present there and represents a touch start and touch end event. And a sketch is sequence of those strokes present there. Here comes the Doodle UINet, and it's use the same Google Quick Draw convention, have 10,000 drawings for 16 UI element categories, focusing only on Android built-in elements and custom design images. It presented card worker with a stylized target image to draw that UI element, so it have a single drawing style. Next is Rico screens and their annotation. Rico is a corpus of huge screenshot of Android UI screens, and each screenshot have a view hierarchy of the UI elements present there. It also contains information like XY coordinate, visibility, text, and other properties of those UI element. Liu et al. Further extended this work by manually categorizing those UI elements into 25 UI element component types. He further classified icon component type into 135 classes and text button into 197 classes. This is an example of a favorite icon and the map type text button in those annotation. Among the 72 screens mentioned in the Rico paper, we collected only 66,000 from their website, and PSDoodle only considers 58,000 screens because rest of the screens have only one element spanning across the whole screen like image, text, or web view, and it was hard for PSDoodle to recognize screens with such one UI element present through the whole screen. There's also some inaccuracies in these Illuator's labeling, like some UI element labeled as input or image, but it has a visualization of star, checkbox, or search. So use some heuristic patterns, like if the UI element is labeled as input or image and have a containers Android class as rating bar, then it visualized as a star as shown in here. So PSDoodle relabeled them as a star. PSDoodle right now supports 7 out of 25 UI element component type like checkbox, text button, switch, slider, image, and text and icon. PSDoodle have also support for 15 icon classes among 135 by Lewis icon classes. This is covered by Doodle UINet and QuickDraw, and rest 120 other class can be represented through a placeholder icon, which is cloud at this moment. From Rico datasets, we created a dictionary, and we also use the 58,000 Android screenshots as a search result for each sketch query. This is the PSDoodle query language. It shows these 16 sketch classes from this Doodle UINet and 7 from this Google Quick Draw. It's shown as a cheat sheet to the PSDoodle user. As PSDoodle's query language, it shows that it supports this stylized Doodle UINet and flexible Quick Draw style. Future work can be support more icon classes, which can be done by collecting more samples representing those classes. So when the user start to draw a sketch, he treat each stroke belonging to that class until it finished drawing that UI element. And right now our tools recognizes these icons or non-iconic UI elements. It also supports some nesting, like putting other UI elements within this container, or compound UI element like text pattern, where you draw a container and within that container there's a squeak line. For UI element Doodle recognition, we employed a deep neural network, and it detects the UI element class from these strokes. We trained the CNN part with 23 different Google Quick Draw classes first, and then trained further on the Google Quick Draw 7 class and Doodle UINet 16 class of PSDoodle, and achieve an accuracy of 94.5% on the test data. This is a drawing canvas, the UI element sketch, the top 3 prediction buzzed by this recognizer, some passive functionalities in the web interface, and when user presses an icon dot button, it invokes a new search query. After finding all those components or merging some compound component present in those Doodle, PSDoodle ranks these 58,000 screens and boost screens that have rare UI elements through their inverse document frequency. PSDoodle considers 3 levels of screen resolution for position matching between sketch and corresponding request screen. So scale 3 considers position match for the whole screen, and scale 2 divides the screen into a 3x2 tiles for position match, and scale 1 divides the screen into 6x4 tiles. As scale 1 considers more precise location matching, it implies more visual similarity between sketch and the request screen. This is the part of the algorithm that focuses on scale 1, scale 2, and scale 3 matching. This is the visualization of the algorithm of PSDoodle. For each UI element present in the sketch, it uses the Rico dictionary to extract those screens and give score based on their position in the tile, or element resolution, level, spanning, and number of elements present in those tiles. Next, the 5 hyperparameters of PSDoodle, which controls the contribution of those scale, level, resolution, spanning, and the UI elements presence. We collected 30 sketches from 5 computer science graduate students representing 30 different request screens. These screens have at least 2 different PSDoodle supported icons, and it was never used for the evaluation purpose. Then we optimized those hyperparameters with Grid Search CV to obtain higher score for that target screen. We ended up with these parameter values, and as you can see, it gives more weight to scale 1 match, which implies higher location similarity between sketch and the request screen. For evaluation, we consider 4 research questions, like the recognition accuracy of partial UI element sketches by PSDoodle, the retrieval accuracy of partial screen sketches as a top 10 accuracy, and compare it with state of the art. And we also want to visualize how many UI elements present in this participant's sketch versus state of the art, and how fast is PSDoodle at a similar top 10 accuracy with the state of the art. We use top 10 metrics as it is easy to calculate by showing target screen and determining where it presents in the search. And it is most popularly used for retrieval task, and it has a correlation with the user satisfaction. For the experiment, we consider 50,000 request screen from this 58,000 that have 2 or more PSDoodle supported UI icons. We randomly selected 30, 26 of them has also present in the SWAT datasets. We hosted our work on a AWS and told each participant to participate through their personal laptop or desktop. About the participants, there was 10 CS graduate and undergraduate student. They don't have any UI and UX design training. 5 of them have experience with app development, with some kind of app development, and 5 never developed any app. Each participant spent around 9 minutes on the PSDoodle interactive tutorial. Then we told them to draw 3 screens and spend around 3 minutes for a target screen or until it appears in the top search results. We recorded their sketching time and query results. We also observed their performance through screen sharing, but we never interacted during their participation. For the research question 1, we chose the confidence levels of PSDoodle with each stroke for 2 random samples from 2 different categories. As you can see, it sometimes predicts those classes before it reaches to the final stroke. So a user can transmit their intent with fewer strokes. It happened for the several classes, like average avatar sketch is 3.8 strokes, but PSDoodle become confident with 2.9 strokes, and top 3 with 2.3 strokes for those test data. Sometimes those participants often sketched until that element ranked in the top 1, or sometimes they selected the top 2 from the second or third from those selection and stopped. For baseline, we use SWARE and its follow-up work. SWARE use some convention for their drawing, like represent image with cross square, where our PSDoodle uses a JLine window. They represent the text with some word templates or squiggle line. They collected 3,800 sketches, trained a deep neural network with this sketch screenshot pairs. Their average sketching time was 246 seconds. Their top 10 accuracy was 61% reported, but their follow-up work reported a 90% accuracy on the top 10. This is the example of request screen and their SWARE sketches. For research question 2, we want to highlight on top 10 search accuracy. And we see that we have 34 total participant sketch, 3 from all the participants, and 4 users attempted one additional time. So we yielded 34 total participant sketches. Among these 34, 30 times the screen appeared in the top 10 results, which shows that it is significantly higher the SWARE compared to the SWARE follow-up work. Among the 4 sketch screens that did not appear in the top 10, it was due to request wrong element level representation in the Lueto's leveling, and sometimes due to human error. And we want to see the top 10 performance of PSDoodle, as PSDoodle used interactive style, SWARE processor complete screen. We see that from this 34 participant sketch, the average number of icons is 5.5. Compared to SWARE has a 21.1, which is significantly lower. We also do a side experiment where we converted the participant sketch into a raw pixel format, removed 8 sketches that use cell window for custom image. We provided to SWARE follow-up work, but SWARE follow-up work fails to rank any 26 targets in the top 10. For the research question, we are going to visualize how our tool is interactive and fast compared to state of the art. So this is the sketching time for these 34 sketches by the participants. The average time for PSDoodle is 108 seconds, where SWARE is 246 seconds, which shows that PSDoodle twice faster than the SWARE. When users submit a query and the screen results appears in the PSDoodle, it takes like less than 2 seconds, and the total sketch recognition time is less than 1 second, and singularity calculation and screen ranking time is less than 1 second on local machine and the AWS website, which supports its interactiveness. This is the link to the repository and the acknowledgements. You can try our tool here. Thank you.